All right, guys, so we're going to move on to U3A3. So U3A2 is binomial distribution. So yesterday or last day, we looked at binomial distribution. That's when we had trials that were independent. So things like rolling dice and that sort of thing. And in real life, there were things like where you have a huge population, and I know that 10% of the people are colorblind, for example. You being colorblind has no effect on the probability that I'm colorblind or the next person. Okay, so those are independent trials, and they form the binomial distribution with Bernoulli trials and that sort of thing. So I hope that went well. Now we're moving on to this, which is the hypergeometric distribution, which I always found intimidating as far as its name goes. But you already know this. So this is not new. Maybe you don't know that you know it, but you do know it. So here we're looking at dependent trials. So the example that we've used in the past are things like cards. So if I take a card out of a deck, the deck itself now has changed. So if I take an ace out of the deck, the probability of getting an ace on the next draw will be lower because I already have an ace out of the deck, and et cetera, et cetera. Okay. So those are dependent trials. That's what this is all about, hypergeometric distribution. So the example that we're using for here that I'm going to follow through with is this one here. I just took this from the note. And what we have here is 25 students. 15 of them have a license. So then 10 don't, right? And if that's the case, the question is, what's the probability that a certain number of them have a license? So I'm just going to we're going to take we're going to choose 5 at random. So I'm going to just do an example here, and then you can just use what I'm going to show you to move forward. So the equation itself is written over here. Let me get to it. So the equation itself is right here. If you want to find the probability of something happening, we've already kind of done this, right? But now it's this guy right here, which it doesn't really help anything because it's kind of complicated. But I will show you how to use this. Okay, and then from there we'll just do the last thing here, the expected thing. So again, not too much for this. So if I go here, we have 25 people. 15 have a license, okay? And then that means 10 don't have a license. So I'm going to do L primed here. So that's 15 total, 25 total. 15 have a license, 10 don't have a license. And the question is, if I take 5 at random, what's the probability that we're going to have a certain amount that have a license? So I'm just going to say, what's the probability that 2 have a license, okay? So we want to find out that I'm taking 5 at random out of the class, and we're then going to look at what's the probability that exactly 2 have a license. Okay, so to do that, what we do, so this is dependent because when I take a kid out of the group, as soon as I take one out, right, what's left over, if he has a license, now I'm down to 14 kids with license. If he doesn't have a license, I still have 15 with license, but I only have 9 without a license. So each kid I take out changes the composition of the next group of kids that I'm choosing from, okay? So that's why we call it a dependent event, okay? So now I want to have exactly 2 with success. So of the 15 kids with a license, I'm going to choose 2 of them, all right? And then that means then of the 10 kids without licenses, I'm going to choose 3 of them, okay? So where do these numbers come from? I have randomly chosen this as being the question I'm looking for. I want 2 with a license, therefore 3 have to have a license because I'm taking 5 out. And on the bottom, what I'm doing is choosing 5 of the 25. You've done this before. When we talked about probability when it came to cards and things like this, we had these guys are successful, these guys are not successful. So what am I doing in general? So on top is the number of ways of success. On the bottom is the total number of ways to do something. I'm choosing 5 kids out of 25. That's this, 25, choose 5. And of those, I'm choosing 2 of the 15 that have license. I'm choosing 3 of the 10 that don't. And you throw this in a calculator and you get a number. Okay? If you want to look at the distribution, all you do is you go through all the different combinations here. You can have 0 with a license, so this would be 0, that would be 5. You could have 1 with a license, that would be 1, that would be 4. And you can go all the way up to having 5 with a license, which would be 5 and 0. And then you could graph them and use Google Sheets to help you with that sort of thing. Okay, so that's all it's asking. The last thing we want to look at here is the expected value. So give me 1 second here. All right, I just cut and pasted that real quick. So this is from the note, but I want to write all over it. So, okay. So that's the formula here that we used earlier. Okay. So you have all these letters here and that sort of thing. But just to go over here, the number of successful objects is A. Okay, so that would go here. So success in our case was license, so that's your 15. Okay, n minus a is the total number of objects, subtract the number successful. Okay, so that is 25, subtract 15, which is 10. Now, you can, sometimes they call it something else like the number of failures. You could do that or just leave it as is. So this guy is 25 because that's our total number. Okay, what I have here is 15 people with license. This is 25, subtract 15, which is 10. And then the next part is I want to know the number of successes. I said 2 for my example, so that'd be 2. And then because I'm choosing 5 kids, that's your R. So 5 is the number you're choosing in total. 2 have success, 5 subtract 2 is 3. And that's how you use the equation itself. Okay, so you can either write it out like that or just kind of get used to using it. The last part here is the expected number. And this one makes sense. What you have is you have the number of successful objects divided by the total number times the number of things you're taking out. So for example, in our case, what you're saying is 15 out of 25 things have, people have a license, and I'm choosing 5 of them, and I want to figure out what the expected value is of the 5. So you go 15 times 5 divided by 25. You can do it like this, where you divide first or multiply after. It's the same equation, right? This has just been moved to the top to clean it up. Okay, so let's say, for example, another example, I'm going to take 52 cards, and I want to know what's the probability of getting, let's just I'll make a question up right now. If I have 52 cards and I'm going to choose 5 of them, and what's the probability of getting all 4 aces? Okay, so that's a wacky question, but let's say I want to get 4 aces right off the bat. So what you do is, let's just make our equation here. I have 52 cards and I'm choosing 5 of them. Okay, and of the 4 aces, I'm choosing 4 of them. So there's only one way to do that. I guess 4 choose 4. And there's 48 non-aces. That's 52 subtract 4 is 48 non-aces. And of those, I've chosen 5 cards and 4 of them are aces. So I have to choose exactly one of the other cards. So you would go ahead and figure that out as the probability. What's the expected value of the number of aces? Okay. So there are 4 out of 52 cards are aces. So this is the number of aces, or that's my A, the number of successful objects. 52 is the N, which is the total number of objects, and I'd multiply that by 5, which is the number of cards I'm selecting. So you would go ahead and figure out what that is, and that's your expected number of aces, which is less than 1. Okay, so that's how you use the equations. Go ahead and play around with the Google Sheets again. Once again, they are Google Sheets. Getting used to Google Sheets is kind of important in this class, so enjoy that. And hypergeometric, binomial, I think they sound harder than they are, but they're not too hard. Okay, send me an email if you have any questions. I'm not going to make a video on the last one. I'll just continue it right now. So let's just go back to this real quick. If I leave this, let's see if this works. Escape. Yep. So the second part of this week's work is selecting the appropriate distribution. So there are 3 types. There's binomial, hypergeometric, and uniform. Some of these can overlap. Uniform can be also binomial and hypergeometric. Definitely can be binomial. I think it can be hypergeometric too. But the key is, how do you know which one's which? Remember, this is where the probability is always the same. Okay, so rolling a die and looking at just the face, 1 in 6 chance, 1 in 6 chance, 1 in 6 chance. Binomial and hypergeometric, that's your big comparison. Are the trials independent? Okay, so sometimes that's easy, right? When you're looking at like rolling a die, that would be binomial, because each time you roll it, it's different. Hypergeometric things like cards, for example, once you take a card out, it is not the same. But once you're looking at people, it can be confusing. And the question is, are you looking at a group of people and taking those people out of the group of people? Okay, so for example, when we look at the classroom question with license, no license, once you take a person out of that room, it now alters what's left over. So that would be a hypergeometric question. A binomial question is, you have a greater population. Once you look at somebody from the greater population, looking at that person doesn't materially affect the probability of the next person getting something. And if you go, no, it does, I'm not going to argue with you, but we're gonna say that it doesn't. Okay, so it's independent. All right. So then go through it, and this is just like, which one should I use? Binomial, hypergeometric, uniform. So these questions are a little more difficult, right? Because you did a whole section on uniform, you did a whole section on binomial, and you did a whole section on hypergeometric. And the homework for each day was just on that. Now it's kind of thrown at you which one is the one to use. All right, take care.